So, we have been on this course of the calculus for quite some time, calculus of one variables. We had tried to be very different from the traditional courses, but some traditional things have to be learned, they cannot be thrown away so easily, and as a result of which I would like to tell you the traditional things that we do, specifically computing areas, computing volumes, etc., using the definite integral, and that is exactly what this section, this part of the talk. See, there was, if I look back at the course, we made it with some thought, but as the course progresses, as the course evolves, in my mind things change. I think that okay, sometimes I think okay, this must be told and this must not be told. So, in that way you have certain things which followed the course, certain things which didn't follow the course, but overall I tried to do something which would be more novel than a traditional course. It is not just funny to talk about traditional things which you can find in any book, any course. You will just open the YouTube and find such things, to tell things which are not really there, you cannot find it anywhere. That is what makes the difference. For example, when we will learn Taylor series, we will see how that can be, or Maclaurin series, we will see that how that can be applied so nicely to show, for example, that pi is irrational. So, those sort of things are not done in a traditional course, and that is exactly what we are going to do, for example, and show that pi actually differs from 22/7. 22/7 is actually bigger than pi. So, strictly bigger. So, that is exactly certain interesting stuff that which is not done in traditional courses would be done here. So, when you learn to compute areas, one of the first things that question arises, and that was also taught in many standard courses, what is the area under this curve, that is y equal to sin x when so this area, you see, if I am walking on the counterclockwise direction, the area is always on the left. So, this area would be actually positive, while this area when taking the counterclockwise direction it is on the right. So, that area would be negative and they would be equal and they will cancel. So, basically if I want to tell you, if you just compute the integral, simply writing that this is nothing but it will be 0, just see that this will be 0, but this actually has a more general structure. This result happens because of a more general structure. There are two classes of functions called odd and even. So, f is even if you have f of x is same of f of minus x. Example, for example, f x is x square. So, another is f is odd, that is that f of x, f of minus x is minus of f x. Here f of, okay, we will write it both sides minus. Here f of minus x is f x, here f of minus x is minus f x. So, this is a function which has symmetry on both sides, and here it does not, in this case it does not have the symmetry, sort of anti-symmetry, x is a cube, for example. Okay. So, When you put minus x instead of x, it will be minus x cube. Another example is sin x. Cos x is an even function, a sin x is odd function. For even function, it is very important that for you to know at the very outset that if my area, my range of integration is symmetric, that is minus a to plus a, right, with 0 in between, then this is nothing but, once it is even, so this is nothing but twice of but if f is odd like the one in sin x, then you will simplify, find that and that is exactly what you see here. Another very typical type of situation arises when you really have to look into the area between two curves. For example, if you have two curves fx and gx with the relation that fx is greater than gx at least on the given interval of integration, right, then at least for all x in AB. So, what is the area between the two curves between A and B? So, it is a situation like this. So, maybe this is my A and this is B. So, this is F and this is G. So, I am essentially trying to know what is the area between. Of course, you understand I compute the area under whole of F and under G and then subtract the two areas and that is what I will get. So, of course, you will have so the area in this case is A to B Fx minus Gx dx. So, from Thomas's calculus we will take some examples to tell you what how to handle such a situation, right. So, as an example, let us see. So, the first example will say that, okay, find the area between the parabola and the line y equal to minus x. So, this example is from Thomas's calculus, a new name of the famous book Thomas and Finis, Calculus and Analytic Geometry. This is one of the standard texts all over the world for basic calculus courses at the undergrad level. So, here what am I supposed to do? Let me see. So, let me try to graph this parabola first. I insist that you always try to do graphs of functions. So, if this is x and this is y, so if you have 2 minus x square here So, if x is 0, y is 2. So, the graph is like this. So, the parabola should be something like this. So, and when y is 0, x is root over 2. Then y is 0 and the x square is 2. So, x is plus minus root over 2. I am just drawing it. It need not be the exact root 2. Okay. Now, I need to know at which points the curve is intersecting, right, at which point this curve y equal to minus x is intersecting. So, y equal to minus x is the line this, passing through 0. So, y is equal to minus x, okay. Where does it hit it? So, where does it cut the parabola? It cut the parabola somewhere here, right. So, what are those cases? So, put y equal to minus x. That will imply x square minus x minus 2 is equal to 0. X square minus 2x plus x minus 2 is equal to 0, which gives me, what does it give me? X into x minus 2 plus 1 into x minus 2 equal to 0. So, it gives me x is equal to x plus 1 into x minus 2 is equal to 0. So, the points where the parabola intersects this line is when x is equal to 1, sorry, x is equal to minus 1. So, here I have two solutions, x equal to minus 1 and x is equal to 2. So, here it intersects, obviously not here, it just goes down like this and intersects somewhere there, 2 somewhere here possibly. So, if I want to draw the graph more clearly, instead of drawing it so big, I would rather now draw this graph. So, now I have that in these two parts minus 1 and between x equal to minus 1 and x equal to 2, the function value of the parabola is always out the function value of y equal to minus x. So, if I draw this graph, so it will be something like this. So, here is your parabola symmetrical. So, y equal to x, it is cutting at 1, something like this. So, this is what we have to figure out, this area. So, what we will now do? So, our tool is very simple. So, f is 2 minus x square and y is minus x. So, it is 2 minus x square minus x. So, the area A is integral from minus 1 to 2, 2 minus x square minus a minus or minus x is plus x dx. So, that is the range. So, now if you integrate out, I am not going to integrate out, I will rather ask you to check the answer, it is 9 by 2. So, another slightly more difficult example which will be again from Thomas and calculus, I will show you two ways of working with such things with that particular example at least, but so let us look at another application which says find the area of the region in the first quadrant bounded above by the curve y equal to root x and below by x axis and the line y equal to x minus 2. So, I am supposed to find, so this is your y equal to root x. So, when it is 2, this is root 2, so this is 2. And through 2, the line y equal to x minus 2 passes, because when x is 0, y is minus 2, and when y is 0, x is 2. So, the line definitely passes through 0 minus 2, that line y equal to x minus 2 definitely passes through, for example here it passes through, so this is 0 2 and this is, sorry, this is 2 0 and 0 minus 2. So, this line just passes like this, right. So, it must be intersecting the curve somewhere. Where does it intersect? Where does this line y equal to x minus 2 intersect the curve? So, when is x minus 2 equal to root of x? What is that value of x? Answer is very simple, you do not have to solve it, it is 4, because if you have x equal to 4, then it implies x minus 2 is 2, and if you have x equal to 4, it implies that root x is also equal to 2. So, that is it. Root x means positive root x only, we are not looking to the negative plus, we are not writing minus root x, because if you write that, then root x does not remain a function, right. So, basically now my job is the following. So, find the area under the curve. I am supposed to, no, this point here, but now I am supposed to find the area only in the first quadrant. So, this part is forgotten. So, I just have to find this area. Which means I am finding the area from 0 to x equal to 4. But people will make a division. What division they will make? See, people will divide like this. First they will say, okay, just take the area of root x, find the area, take the area of root x from 0 to 2. And then add this area, but here from 2 to 4, root x is bigger than x minus 2, y equal to x minus 2. So, between 2 to 4, you will do root x minus x minus 2. That will be the way to compute it. Okay. So, I will just write the answer, I am not going to write down the details, and so answer here is 10 by 3, because we do not have so much time. Now, you can do it in a slightly different way also in this particular case, because if you observe it very carefully, what will you have? This is a triangle actually. This triangle has length 2 and height 4, this particular triangle. This triangle, what is the area? So, area of this triangle is equal to half of base, which is of length 2, into the height, which is 4. So, it is 4 units. Okay. And what is the, so what I will do to find this part of the area, I will compute the area under the curve from 0 to 4 and then subtract this triangle. I will get that same area, right. So what I will do here is basically then I can do 0 to 4 root x dx minus 4. So let us see whether we get the same answer. So if I do root x means it will become 2 into 2/3. 2/3 am I doing the correct thing? 0 to 4 means 2/3 x to the power 2/3. So it will become, so 2/3, so area is equal to 2/3 x to the power half plus 1, right, 3/2, 3/2, sorry, 2/3 x to the power 3/2 from 0 to 4 minus 4. So 2/3 into 4 to the power 3/2 minus 4. So what is happening? 2 into 4 to the power 3/2 means 4 to the power half, which is 2, 2 to the power 6, right? No, 2 to the cube is 8 minus 3 into 4, 12 by 3. So the answer comes out to be 4/3. I don't know why does the answer doesn't match. Answer should match. Is there any mistake here in this? Because that is a natural thing, because I will just have a triangle here. So I take this triangle out from this whole area under the curve, and then only this part is remaining, right? That is what we require. So this area is 2 to 4, which is 2, the length of the base, and other part is what? 4. 4 into 2, 8, half base into area is 4. So subtracting that from 0 to 4, so integrating 0 to 4 under root x is x to the power 2/3. 0 is 0, 2/3 into 4 to the power 3/2, 2 square. So it will become 2 cube, which is 8. So 3 into 4, 12. So 16 minus 12 is 4/3. Where is the mistake? Then how do we handle this? Can we make a small checkup of this?
Area 10/3 or 10/3? 10/3 or?
No. Area is 10/3 according to the book, but here it appears to be 4/3 if you go by that method, but they should match, right? So here it's let us make a check. So here it will become, what does it become? 3/2, sorry, 2/3. X to the power 3/2 from 0 to 2 plus 2 to 4 root x minus x plus 2. So let us do the computation. So if I do the computation here, let me see what I get. So I think this should match, because I do not see any logic why it should not match, right. So these are the trials. So in mathematics, that is the way you do. Maybe I am making a mistake, but that is what I see. This is the whole area under the curve. This is the full area, and I have just taken this triangle out, which is giving me the remaining area, and that is exactly the most simplest way to look at it, knowing that the area of the triangle is. That is a mistake. The answer is correct. The answer is correct. This height is not 4. This height is actually 2, because it is root of x, no. So this height is 2. So this height is 2. So this area is 2. So it is 2 is the area. So if I have 2 here, so I told you some calculation mistake. 2 into 8, 16 minus 3 into 2, 6. 16 minus 6 is 10, 10 by 3. So, you see once you are sure that the mathematics that you are doing is correct, the answer has to match. So, the answers anyway match. So, both is 10. So, this is also equal to 10 by 3. Sorry, that was a mistake, because this is 4, this height is same as the height of the function value at x equal to 4, which is 2, where the function is f(x) equal to root x. So, here is an example how you two ways to do the same problem. Obviously, the one we had done is a much simpler one by looking at the geometry immediately, but here in the book they have followed standard ways of doing things, but does not matter. Though this area which I did it, I find that at the end of this chapter they have also done the same thing, but okay. So, two different ways to do the same problem. I would like you to try, for example, this proof. It is sometimes fun to do proofs. So, if f is an odd function, how would you show that it is 0? So, one approach could be that you look at f(x) dx as from minus a to 0 f(x) dx plus 0 to a f(x) dx. So, I am not doing the other part which is already done for so this is an exercise asking in Thomas and Finney and Thomas's calculus, asking you to prove this. So, what do? You substitute minus x equal to minus x basically, or x equal to minus z possibly, x equal to minus z. So, dx equal to minus dz. So, x equal to minus z. So, this becomes f of minus z minus dz. So, when x equal to minus a, this is a, when x equal to 0, it is 0. So, a to 0 plus 0 to a. Instead of z, I can also write fx dx. Now, you can say why z and x? These are dummy variables. So, do not bother with dummy variables. You can just write it as f of minus x dx plus 0 to a f of x dx. Now, you see how the reasoning goes, but because this is odd, f of minus x is f of x is minus x. So, okay. So, this will become now will become a to 0, sorry, it will become 0 to a because of the minus here. So, this will become f of minus x dx plus 0 to a fx dx. But you see f of minus x, the function being odd, it is minus of fx. So, this is nothing but 0 to a minus of fx dx plus 0 to a fx dx, which is equal to 0. That is it. That solves the problem actually. So, you see we had some discussion of how to find areas, what are the relations, a little bit of proof at the end, so that you would have some time. So, with this we will stop, and in the next class we will try to discuss more about these applications. For example, finding volumes, how will you find volumes. So, this will come in the next lecture, that how would you go ahead and find the volume of a object, right. So, let us that would be very important. So, how just you can use this integration to find the volume of an object. So, we will learn some stuff for finding the volume of a sphere, of a cone, of a cylinder, and all these things, and let us see what would how we go about it. So, we will take time and In the next classes also we will keep on doing this integration, volume of cylindricals, shells, and these applications of how definite integral just of single variable can be used to find a lot of good things. So, maybe some of the applications they have to physics, these sort of things. So, now for 2-3 classes, 4 classes we will discuss about applications, how things can be applied. So, we will come back to the next class and we have discussed volume, we will discuss surface area. So, this will continue for 3-4 more classes and then we will go to sequence series, Taylor's theorem and all the stuff. So, some idea about power series, and we will come to all those things in possibly in the last section. And so, we have 10 lectures more, of which I guess if we do not take this lecture, last lecture into of which I guess couple of lectures would be 3 lectures or 4 lectures would be on integration, and the remaining lectures would be really on power series, sequence and all those stuff. So, we will come back to this very soon. So, we will start looking at volumes in the next lecture.